So the unit you did in grade 12 on combinations, permutations, and the binomial theorem comes up again in the IB course, except they don't have all the extensive permutations and combinations questions. So you won't get on your exam, you know, the question where Sally wants to sit with her two friends around a table, but she doesn't want to sit beside Brad, and there's an empty chair. How many ways can this be done? Those really complicated questions which made you think and think and think from last year. They are not on your IB exam. But you do need to know the combinations formula. And the combinations formula from last year in pre-calculus, we wrote it like 5 choose 3. And the formula on our formula sheet was the n factorial, or n choose r was n factorial over r factorial, n minus r factorial. IB uses this notation instead of NCR. They use brackets with an n on the top and the r on the bottom. There's no line, it's not a fraction, but it means combinations. So this 5-3 means 5 choose 3. This 10-2 means 10 choose 2. Plug them into the formula and evaluate. So I want you to try to do all of these without your calculator. Mental math startup. What we can do is we can start expanding the biggest number. 5 factorial is the biggest. It'll be 5 times 4 times 3, and then the 3 factorials would cancel out. Right? So then your mental math, it just has to be 20 divided by 2 rather than 120 divided by 6 divided by 2. Just a little bit easier. Especially in the next one. 10 factorial over 2 factorial, 8 factorial. You don't need to know what 10 factorial is, but if you start expanding the bigger one, 10 times 9 times 8 factorial, then your 8 factorials will cancel out. And then it's just 90 divided by 2, 45. We notice that 10 choose 2 and 10 choose 8 are the same. The formula says they're the same. But if we think about what does a combination mean, it means choosing something where the order doesn't matter. So if I take 10 cards, and 4, 5, 6, 7, 8. If I take 10 cards, every time I make a group of 2, I'm left with a group of 8 where the order doesn't matter. So choosing this group of 2 is like choosing this group of 8. And that's why 10 choose 2 and 10 choose 8 are identical. Anything choose 0 is going to equal 1. We can look at that from the formula. You can see your 7 factorials disappear. And you have to remember that by definition, 0 factorial is equal to 1. So you have 7 cards. You make a group of 0. There's one way to do that. Keep the 7 cards by themselves. Make the group of 0 over there. And this one for mental math, once you see that you can expand the bigger one, which is biggest, 100, until you get to the 98, they'll cancel out. And you just have 100 times 99, 9900, divide by 2, 4950. All right, we've got, oh, before this, we've got our Pascal's triangle in there. I'm going to just see if I can add that slide with a picture. Does the camera button work? No. There is Pascal's triangle. With Pascal's triangle, what we have is you can find the next row by adding up the numbers above it, right? So if I want to find this number 10, I can get that by adding 6 and 4. And Pascal's triangle is super fascinating with all the patterns that are involved in it, but one of the patterns is that every single number in Pascal's triangle relates to a combination. And those combinations relate to the coefficients in x plus y, or binomial expansions. How do they relate? Well, x plus y to the 5 means this. X plus y, God, we only used 5. X plus y, right? X plus y. And when you're multiplying this all out, every single thing gets multiplied by every other single thing. So it's like one massive, I don't know, like in English we use FOIL when we just have two for the first, the outside, the inside, and the last. This is it's the acronym for this is just all the way through, yeah. And so one of the possibilities is all of the first ones get multiplied together. If that happens, you're going to get an x to the 5. And there's only one way that that can happen, and so that matches up with this one here. Some things to remind yourself from last year, that if you have x plus y to the 5, when this is all expanded and simplified, there's going to be 6 terms. There's always one more term than what the exponent is. One of the ways that I like to remember some of these things is take x plus y squared, which is x squared plus 2xy plus y squared. Something easy. It has 3 terms. That can help remind you that there's one more term than the exponent number. Okay? And because there's 3 terms, we can notice that we're using this row right here for the coefficients. 1, 2, 1. So with x plus y to the 5, with 5 terms, I go to the row that has 6 items. And so after x to the 5, we're going to get 5x to the 4y. And then we're going to get 10x cubed y squared, then 10x squared y cubed, then 5xy to the 4, and finally 1y to the 5. So we can expand this completely using Pascal's triangle for the coefficients and noticing a pattern that in every single term there has to be 5 items. Because if you randomly choose something from here times something from here times something from there times something from there times something from there, that will create one term. And the one that I picked had 3 x's and 2 y's. The red one would have 3 x's and 2 y's. So one thing we notice is that our exponents in each term add up to the 5 as well. Mathematically, why does it work out that this is 5 choose, 5 choose? On your formula sheet, I'm trying to remember, yeah, I think it goes 5 choose 0, 5 choose 1, this one's 5 choose 2. Why is that 10, 5 choose 2? If I think about all the arrows I could draw going across, this one right here is the situation where I have 2 y's. How many different ways could I draw arrows that had 2 y's that are all different? 10 ways. And why is it 10 ways? Well, I have 5 y's that are in total, and I need to choose 2 of them that are going to be in the multiplication. Whatever's left will be the x's. The order doesn't matter, because if I choose this y and this y, that's the same as choosing this y and this y. And so that's the reason that combinations comes up in this formula. You don't need to know the reason, but that's where it comes from. And so we can expand something using Pascal's triangle and the combinations that are involved with it. Okay. I'm just going to show you one other, because Pascal's triangle has tons of cool stuff in it. I'm just going to show you one cool thing in it. Would you like to see powers of 11 or Fibonacci numbers? Fibonacci numbers? Fibonacci numbers in Pascal's triangle can be found. Ooh, I'm going to make a rectangle like that. I'm going to take that rectangle and rotate it. All right. So if we move this rectangle down, you see the number 1. The next time you see a number, it's the number 1. The next time you see numbers, oh, you see 2 1s. 1 plus 1 is 2. The next time you see numbers, you see a 1 and a 2. 1 and 2 is 3. You know Fibonacci numbers? Should I write them out again? 1, 1, 2, 3, 5, 8. The famous numbers where you add the 2 previous ones to get the next one. Okay? So if I move this rectangle to the next, I see 1 and 3 and 1, which adds up to 5. The next numbers we see, 1, 3, and 4, well, that adds up to 8. I move it again, 1, 5, 6, and 1, oh, that adds up to 13. If you keep doing this, you'll always get the next Fibonacci number. Oh yeah, I'm sorry. I have to show you powers 11 as well. It's just too cool. If you think of this as an entire number, this is 11. This is 11 to the 1. Ooh. 121 is 11 squared. 1331 is 11 cubed. 14,641 is 11 to the 4. And then we have a problem because we have tens in there, right? But if you think of these as places, and 1, 5, 0, carry the 1 to 11, carry the 1, sure enough, that is 11 to the 5. Okay? And if you do that with the next one, 1, 6, 5, carry the 1, carry the 2, carry the 1, there we have 11 to the 6. Fancy. That's crazy, eh? So Pascal's triangle has lots of really cool things in it. Those are just a couple. What you have on your IB formula sheet looks like this. Okay? And this is in comparison to your grade 12 formula. Okay? In grade 12, you had this formula on your formula sheet for a plus b to the n. In the IB, for a plus b to the n, they give you this very long formula. They are the same. The IB one is combining sort of like if you did the whole thing, what it would look like as a pattern. But this part of your formula from grade 12 is just built in to this part right here, the random one that they put in the middle. But instead of n choose k in this format, they use n choose r in the other notation. So instead of n minus k, we have n minus r. In your formula sheet, right, this was for term k plus 1. So if you were finding term 5, k was 4, because 4 plus 1 would make 5. So you remembered that, or you saw that in your formula to help you determine which term you're finding. On the IB formula, it's not there, the k plus 1. but it's kind of built in because this is your term 1. This is your term 2, where this is 1 less. And so you would know that this would be term r plus 1 because there's an r underneath and that number is 1 less. But it's a little bit hidden in there, that k plus 1 idea that was on your formula sheet from grade 12. So using the formula, find the 7th term. Well, the 7th term, the r value would be 1 less. It would be 9 choose 6. Your first term is 2 to the x, 9 minus 6 there, negative 3y to the 6. Simplify each thing separately. Keep them in brackets so as not to make any mental math errors, and then combine everything in the end. So lately on both grade 12 and the IB exam, sometimes they've been asking you to find the next row in Pascal's triangle or to describe what Pascal's triangle does for binomial expansion. Not very often, but it has come up. So in this question, they're not telling us which term we want to find. Instead, they say there is a term that has a y to the 12. What is that term? So if we think about the formula, okay, if I think about the formula, I wouldn't have known, take my eraser out, I wouldn't have known, wow, that was an eraser. I wanted this eraser. There we go. I wouldn't have known what my r value is, or in the past, what my k value was. But I know that the exponent is 9, so I know it's going to be 9 choose something. I'm going to just leave that blank for now. I know that my first term is 3x, so it's going to be 3x to the something. But I'm going to leave that blank right now. And I know that I'm going to have negative 4y squared to the something. Now looking at the 3 terms, the first set of brackets is just going to be a number. The second set of brackets just has numbers and x's. My third set of brackets has numbers and y's. I need y to the 12. So the only place I'm going to have y's is in my third set of brackets. And I already have a y squared. I would need a 6 here in order to make a y to the 12. Then I think back to my formula. If there's a 6 here, that's r, there would have to be a 6 here. And the value that goes in here is 9 minus r, so this would have to be a 3. Yes? How I got 6 in the previous one? Yes, in the previous one, we got 6 because we're finding the 7th term, and the r value is always 1 less. So the thing that we notice here, this is for tr plus 1. That value underneath is 1 less. All right, so now going back to this one, we know it's term 7. Again, we can solve for each thing individually and get our complete answer. All right, this one I just want to walk it through with you completely. So we want to find the constant term in this expansion. So if we think about it, and you can either think about your old formula or your new formula, we're going to have 14 choose something because I don't know which one is my constant term. I have 3x squared. It's going to be 14 minus whatever. I'm going to put r there for now. And negative 1 over 2x to the 5 to the r. We also have to remember what this means. If we have no idea what a constant term is, we're pretty much screwed in this question. The constant term is a term that's just a number. Just like 15, 47, there's no variables in that term. In fact, sometimes people think of the constant term as the term containing an x to the 0 in the expansion. So there's two different approaches to trying to figure this out. Because unlike the previous question when we wanted to find a y to the 12, there was only one place that there was a y. So it was really easy to see that the exponent had to be a 6 to get us the y to the 12. The problem in this one is we have x's here and we have x's here. And they're going to simplify afterwards. In fact, this one's going to give us x's in our numerator, and this one's going to give us x's in our denominator. Some people like to solve the next part by mental math, because it's not, you know that r has to be a whole number, okay? And so it actually does not take very long to do the mental math to figure it out. Usually I say, start with a random value of r. Pick a value for r. 4. So if you pick r is 4, can you see that here you would have 14 minus 4, which would be 10. In our numerator, how many x's would we have? In our numerator, I'd have x squared to the 10. I'd have x to the 20 if r is 4. In my denominator, if r is 4, oh, nice job, good work. If r is 4, how many x's am I going to have in my denominator? 20. What happens with the x to the 20 and the x to the 20? They cancel out. You get an x to the 0, or you get a constant term. So now we already know that's what r should be. Did you do all the mental math, or you just...
I'm a
mental math wizard. Nice. Oh, I lent out my Secrets of Mental Math book. I got to buy a new one and get it back. It's a good book. So that's method 1. After seeing this, you might go, oh, I like that method, right? You can solve it. What happens if you chose the wrong number? Right? If we didn't ask Harry, we asked somebody else, and they said 5. Well, if I had 5, then I'd have 9 as an exponent. X squared to the 9 would leave me with x to the 18 on top. And if I have a 5 and an exponent for my denominator, I'd have x to the 25. That would tell you you have too many x's in your denominator. How do we reduce the number of x's in our denominator? We would have to make r smaller. And probably you would get 4 the next time and get it right. Okay? So that is the mental math way of just thinking about it and figuring it out. I like that way, because for most of these questions, that's not very hard. There was a provincial exam a couple of years ago that said you weren't allowed to do that. You had to do it algebraically. The algebraic method looks like this. We need all of our x's to cancel. We have to make a special note that we ignore all coefficients, or all the values that affect things in front. right? Technically, the constant term would have some number in front times x to the 0. But we're going to ignore that and just think about the x's. So then in this case, I'm going to have in my denominator, in my numerator, x squared to the 14 minus r. And in my numerator, I'm going to have x to the 5r. It's basically the same thing we did with mental math. We're just making it more complicated because we're using variables. And then we use our exponent laws to simplify this. On this side, still x to the 0. Can you see on top here you'd have 28 minus 2r, and on the bottom we still have x to the 5r. What's your exponent law when you're dividing powers? Subtract. So then if I subtract 28 minus 2r, subtract 5r, I'm going to get 28 minus 7r. And once you have both sides as powers of x's, you don't have to use logs. This is the one where if the bases are the same, the exponents would have to be equal, right? So then we get 0 has to equal 28 minus 7r. 7r equals 28. Divide by 7, and we get 4. That is the algebraic method. The third method is a pattern method. You want to find the constant term. So you think about, in term 1, what would it look like? Term 1 would be 14, choose 0, 3x squared to the 14, and negative 1 over 2x5 to the 0. And in the pattern, you're going to say that's going to be some number times x to the 28. Does that make sense? Then you would say, what's term 2? Term 2 would be 14, choose 1, 3x squared to the 14 minus 1, negative 1 over 2x to the 5 to the 1. And that would equal some number, and here I would have x to the 26, x to the 9. 26 minus 5, 21. Thank you. X to the 21. And usually with the pattern method, you do 3 of them just to make sure you haven't made a mistake. The third one would be 14, choose 2, 3x squared, 14 minus 2, and negative 1 over 2x to the 5 to the 2, which would equal some number x to the 14. And in the pattern one, you say, what's happening to our exponents? They're going down by 7. So at this point, term 4 would have an x to the 7. Term 5 would have a x to the 0. And this one would be our constant term. It's term 5. Does that make sense that r would be 4, 1 less? So all 3 of those methods help us find out which term it is. Once we've found out which term it is, so here's algebraic way. Here's this solution for it. Once you find out that r is 4 or n is 4, now this is the only thing, this part here, is what you would have to do in your notes. We need to actually find that constant term. Happens to be quite a small number, right? One of my favorite numbers, under 100 trillion. Oh, it's bigger than 100 trillion. Shoot. Under 5 quadrillion is it's my lucky number, yeah. There's, yeah. Big number. Ooh. I had forgotten that 14 choose 4 was 1001. That's a pretty looking number. Yes. No, it's commas. These are commas. Sorry. We could probably be good to type it all in again just to make sure, but no, there's no decimals. Oh, it might be a decimal. Oh, shoot. Yeah, it is a decimal? Okay, then it is under 100,000. Here we go. .063. Yeah, we are dividing by 16. So someone type it in? Now I'm curious. It is a decimal. Okay, perfect. All right, I want you to do the next couple on your own. I'll put them up so you can check. So the fifth term is equal to this, is given by that. Write down the value of n. So here it's just the recognition that whatever our exponent is equal to what in the combination things at the top, right? 10 choose 4. The 10 choose 4, that 10 comes from the n, from the exponent. Write down a and b in terms of p or q. Well, a would be p, and b, the second one, would be 2q. That one's not so bad. Write down an expression for the sixth term in the expansion. Well, now we can put 10 choose 5, p to the 5. You could expand this and simplify it. That wouldn't be hard. But it just asks for an expression, and this is an expression. So question 5, not so bad. But initially, feels a little bit different because there's a whole bunch of letters involved instead of numbers. Things get worse in question 6. Ready? The expansion of this, the sixth term contains x to the 16. Find the value of n. Now, in your grade 12 course, never were you asked to solve for the exponent. So right away, this is a little bit different. But thinking about that, we can still go about this the same way that we've always done. We can sort of set up our equation. What do we know? We know that we would have n choose 5 for the sixth term. You might even want to write term 6 equals here. X cubed to the n minus 5 and negative 4 over x to the 5. Considering that and ignoring the coefficients, just looking at your variables and their exponents gives us an x to the 3n minus 15 in our numerator and an x to the 5 in our denominator. From there, you can use algebra to solve for n, and you get n equals 12. What I like about this example is the fact that even though you'd never in the grade 12 course solve for the exponent, that never came up as a question, never on an old exam, never in any of the homework assignments. Despite that, you run across a question that's new like this, then you go and say to yourself, well, what do I know? What do I know about the sixth term? How do I set that up? What do I know about the answer? And then work with the tools that you have. And this one, in my opinion, ended up not being any more difficult than, say, find the constant term or find the term containing x to the 3. It's very similar to those questions. Here's another old exam question. What's different about this one? Right? Consider the expansion of this. Sorry, there's a little 8 there. I can move it down. There you go. Consider the expansion of this. The constant term is 16,128. Find k. What's different about this question? There's something outside the brackets. That x to the minus 2. So how does that affect our equation? If we ignored the x to the minus 2, how would the question change? If I took out the x to the minus 2, it would no longer be the constant term. Which term would we be looking for? So that's what the first thinking thing has to have. Sorry? Close. You're very close. If I multiply x to the 2 times an x to the 2, I'll have an x to the 4. And it wouldn't be the constant term. What would it have to be the constant term? Okay? If I just found the constant term in this one, and then I multiplied it by x to the 2, it would no longer be the constant term. You have to find the x to the minus 2 term, right? So if I took this out, you wouldn't be finding the constant term. You'd be finding the x to the minus 2 term. But having that here makes the x to the minus 2 term the constant term. So we set things up saying, here's my expansion. I want to find the x to the minus 2 term. Ignore the coefficients once again. Okay? Now, I introduced the variable n here. You could use r from your formula sheet, would be fine as well. But with that, you can find out that your n value or your r value has to be 6. Which means it's term 7. That in itself would have been a hard enough question. But then we still need to find out what the value of k is. So now that we know that n is 7, oh, of course, I went and erased everything here. My big fat eraser. When we know that we're finding term 7, and we know that term 7 is apparently equal to 16,128, we can solve for k. Technically, I should have the x squared out in front of this. but then all of my x's cancel out because it is the constant term. And you can solve for k. This question was very poorly done on that exam. First of all, that x squared out in front threw a lot of people off. So sometimes say, well, could I solve it more simply? What does that x squared do? It means I'm trying to find an x to the minus 2 term. Then, after finding out which term it is, you still have to find out what k is. I call these questions on the exam, I was at an IB conference once, they're called 6-7 determiners, or 6-7 distractors, because they're going to determine who gets a 7 on the exam and who gets a 6 on the exam. A lot of people, like 90% of people, got this question wrong on the exam. So one of the things that we try to do during the year is push you to see a bunch of these questions, and then you do better on all the other ones leading up to it. I'll put the answers up on video if you want to check it out later.